Howdy everyone, and welcome back. And so we've been talking about electrical stuff for a bit, and sometimes you need to take a step back and look at the picture holistically, because it's very easy to see all these little individual groups, but it doesn't really do much good if we go and we don't know how to use anything, and we don't know how things relate to each other. So we're going to spend some time reviewing and thinking about what the things we've talked about over the last few weeks, but then we're also going to go and apply a lot of this stuff. And usually I prepare a lot of things, but this time I'm just going to kind of go with it. I have a bunch of problems. I'm just going to solve them on the fly. Maybe it goes great. Maybe it goes awful. We'll find out, okay? So we started out, we talked about what happens when you have two charges and they go and sit next to each other. Maybe one's a positive, one's a negative charge. We talked about how they can exert forces on each other. So these would be attracted, they'd pull on each other. So that's one way of looking at it. Another way of looking at it is that this one's creating an electric field, and that's the electric field is the thing that's actually exerting this force F. We also learned that we can find the electric potential from a charge and solve problems this way. And we know that the change in the electric potential has to do with the electric field. So it's the change in electric potential or some change in distance along this site. So all these quantities sort of interconnect. Okay, the relationship between force and electric field, it's very simple. So this Q naught charge would be the charge sitting in this electric field that's being affected by it. So all these quantities are interrelatable, and we can sort of move between them. And sometimes it's easier to do a problem with one of them versus the other. Really, sometimes it's really easy to do with potential. You know, since we don't know derivatives, a lot of times we have to work directly with electric fields instead. But sometimes electric potential can be very easy because it's just scalar. So we learned how to get the electric field and the force from a single charge. That's just Coulomb's law. That's that KQ over R squared stuff. The other thing we talked about is surrounding charges with Gaussian surfaces. And we know Gauss's law, which is the electric flux. So that's my electric field passing through the electric field times the area. So that's at every point you sum up the electric field times this cross-sectional area times the angle between the electric field and the normal vector pointing out at some point. So you sum up all that, and that's going to equal the charge enclosed. You can go back and derive the electric field from a number of examples doing that. So we can think of these as all separate tools that we can use in certain circumstances. So typically what we're trying to get back to is maybe force, but sometimes it might be easier to get the electric field from something. So maybe it's easier to get the electric potential than the electric field than the force. Sometimes we need to get the electric field a different way through symmetry, and that's when Gauss's law comes in. So there's another standard quantity from classical mechanics that we can relate to electrical quantity. So we can do, get back force from electric field by multiplying by charge, but we can get potential energy by also doing the same thing. So instead of this case, we take the electric potential, the change in electric potential times a charge sitting in there. So as far as electric field stuff, that's about all it. But we also talked about capacitors and resistors for a little bit. So again, a capacitor is a parallel plate. That's the typical model we have. But we can have create capacitors that are curved too. Positive charges on one end, negative charges on the other. That the charge on this is equal to the change in voltage times this inherent capacitance, which you get from the shape and geometry of the capacitor. So it's some permittivity constant over the cross-sectional area over the distance. We also know the energy stored in a capacitor is 1/2 Q times the change in voltage. We can always use these two equations to exchange quantities. Maybe we don't know the charge, but we know the voltage and capacitance. We can always take out what we don't know and substitute it in. So we learned how to break things into equivalent capacitors. So we learned how to break things into equivalent components. So we have parallel, we have in series. For capacitors, in series is this 1 over weirdness. So for capacitors, we get this 1 over weirdness. And so, it's kind of complicated, but it's a little more simpler with capacitors in parallel where you can just add them up straight. Okay, what you're doing in these cases is you're replacing a long string of capacitors in series or parallel with one single one. And again, if I take out all those complicated ones, put this equivalent one in here, nothing changes elsewhere in the circuit. It's the same. And we also learn about resistors, which essentially are things that take electrical energy and turn it into heat. They resist current going through them, where current is the change in charge, moving through a point over time. So we learned that the voltage drop over a resistor is equal to the current passing through it times its inherent resistance. We also learned the power being sapped from a circuit from a resistor is the current going through it times the change in voltage. And so stepping back, it sort of looks like a grab bag of a lot of things. In some ways it is, but we have this idea of general fields and electric fields and how they relate to each other. And we just started dipping our toes in terms of electrical components. And that's essentially all we've talked about so far. And so a lot of the tools that we use are going to be pretty obvious. I mean, when we have capacitors, we should probably use this stuff earlier than that. When we have resistors, we should probably use that. Going back in electric fields, maybe it's not so obvious, but hopefully it should get more obvious of which tool to use and the fact that all these things interrelate in the ways that they do. So let's go and take essentially a practice test and see how we do. I haven't really looked at this much, so we'll see how it goes. So maybe I'm a complete hack and I don't know anything, so we'll figure that out pretty soon. We have two metal spheres that are initially uncharged and are mounted on insulating stands as shown. A negatively charged rubber rod is brought close but does not make contact with sphere X. It doesn't make contact. Sphere Y is then brought close to X on the side opposite to the rubber rod. Y is allowed to touch, so it's allowed to touch given consent, then is removed some distance away. The rubber rod is then moved far away from X and Y. What are the final charges on the spheres? So something to note is when you bring in a bunch of negative charges here, on this side, you'll have a lot of positive charges that want to sit here, want to get closer, and negative charges here. So if this is what's the only thing that was existing here, it would just sort of separate it. It would make this little dipole here is what we call it. So the thing is that these charges are actually allowed to move. So they're going to go over and go move as far away as possible. So when they're touching, so they move away. The whole thing overall is electrically neutral because it already started out as electrically neutral. So then when you pull them apart, you have all these excess positive charges, all these excess negative charges. And once you do pull them apart, they'll start spreading out. You know, this will move over here. This will move over. This will move over here. There we go. And, you know, they'll spread out. But then you have a case where now individually they are, you know, not neutrally charged, but together they're neutrally charged. So what are my options? Both are neutral. Okay, it's not that one. X is negative. No, not these ones. Okay, so X is positive, Y is positive. No, so it's got to be this one here. Okay, we have plots in figure 1 and figure 2 show the electric potential energy for the system of two interacting objects as a function of R, which is the distance between the two objects. So you have something sitting like here, something sitting here, and this distance R is what's in between them. So the objects in the systems in each figure are 2 protons, 2 neutrons, 1 proton, and 1 electron. So it's probably not going to be 2 neutrons. Neutrons don't have any charge, so they probably wouldn't make, you know, they interact with any electrical stuff. They probably wouldn't have any electrical energy associated with them. So I'm just going to go cross that off. So any of them that say B, take out those. Just take them out immediately. At least one of these curves is not physically possible. So we should think about that. So what does the potential energy look like? So we can think about one of them creating, electric potential and the other one sitting in it, and that's how we're going to get electric potential energy. So the electric potential created from a single charge is KQ over R. So, you know, that depends what positive or negative, whether this charge is positive or negative. And the potential energy, the change potential energy, is going to be this times a second charge. Okay, and this is we were going to see where we get some signs. So if this is positive and this is positive, it's going to be positive potential energy. So if this is positive and this is positive, you see that we'll get a positive number out here, and it will go as 1 over R in the end. So we write this out here. Be K, Q, I'll just write it as Q1 and Q2 instead of Q0 over R. That's what the potential energy will look like. So if these are both the same sign, this will be positive. It'll be something that kind of looks like this. It'll be 1 over R, so it'll be proportional to 1 over R, which this does look like as an inverse function. Or if these are opposite signs, it'll be a negative sign. So it will also be an inverse function, will be flipped on the y equals 0 axis. So it will look like this. So same sign, opposite signs. What are our options? 2 protons and 1 proton and 1 electron. So this is going to be this one. This one's going to be this one. They're both possible. So so you maybe feel weird. Well, how can you have negative energy? Well, the really only physical thing is the change in energy here. Hey, buddy, what are you saying? What are you saying, my buddy? This is really the change in potential energy here, not energy straight up. But energy is weird when we're talking about fields. You can always skew the entire scale. You could, for instance, you go say that I'm at 1,000,000 volts here and 1,000,000 plus 1 volts here, but the only physical thing is essentially that change in volts. So it doesn't really matter where you say the 0 point is. So it shouldn't really bother us that we have negative energies here. It's the negative change in energy. So I'm saying since this one goes to this and this one goes to this. So this one's interesting. A test charge is placed an equal distance away from the two charges of a dipole as shown in the figure. So we got this bad boy here. In which of the following directions will a negative test charge experience a force? So we have a pretty interesting problem here. We actually don't really need to do any of that math. It's actually really all going to be geometry here. So we see at this point, we have charges, they make electric fields that are pointing outward for them. So this positive charge is going to make an electric field pointing this way at this point. We have look at the negative one, so that makes electric fields pointing inwards. So this one's going to make an electric field pointing this way. So that the fact we have some geometry and the same distance is going to mean that these are the same angles here. And because of the same charge, it's also going to mean that they're the same magnitudes. So essentially what's going to happen is that the y components of each of these are going to cancel out. So all we're going to be left with in the end is this net electric force going this direction. So this is what we actually really need to care about and pay attention to. So when they combine, actually you'll notice if you do some math that the electric field lines will kind of look like this. So every point here, halfway in between, they'll make electric field pointing this way. So we have the electric field pointing to the right. So what direction would a negative charge experience a force? So again, recall the force is the electric field times the charge. So the electric field's going to the right. We have a charge that's a negative. The force will actually be the opposite direction of the electric field. So it actually will be here, G. Okay, we have another pretty fun one here. We have a line of charge, so it's a one-dimensional object. It has a charge density, so the charge per length, lambda, and it has a length L here, okay? So which of the following gives the electric flux calculated over the Gaussian surface as illustrated? So this is actually not going to require that much to do. So recall that the electric flux is the sum of the electric field on all the surfaces and the cosine phi. Okay, so there really is actually only one surface. Okay, so we don't really need to do the full calculus thing because we'll find that the electric field is always in the same direction as the normal vector. So the cosine is always equal to 1. And so that essentially we just add up all of the areas here. So then we get the electric field times the total surface area. So we notice that all the electric field will be going straight out. And so none of it's really going to pass through the ends of the tube. We only have to care about this area in here, that essentially the side of the cylinder, and add up its total surface area. So what is the surface area on the outside of a tube like this? So essentially it's going to be the circumference times a length. So we need to get the circumference, we need to get this length. So it's going to be E. And so the circumference of a circle is 2 pi r. And the length is going to be this L here. So we get 2 pi r times L. We look, okay, what answer looks like that? Not 0. Not this guy, not this guy. It's going to be this guy. Okay, similar problem again, except this time we want to find the charge enclosed. This is actually even simpler. So we just need to figure out what's the total charge in between both ends of our surface. So this thing's got length L, it's got charge per length lambda. So would you believe that the total charge enclosed here would be the charge per length times the length? It's just this guy. There's nothing complicated. There's no cylinders. I mean, just how much charge is here. That's all we're asking. So yeah, that's it. Ooh, we got a fun one here. So consider a solid conducting sphere, radius r, total charge q. So I'm going to assume the charge is uniformly distributed, because I don't think it says in here. Which diagram describes the E versus R, electric field versus radial distance function for the sphere? So this is an application of Gauss's law. So to me, it seems pretty obvious that, well, actually, it seems really obvious that it's always going to be 1 over r squared on the outside, and that's actually all our only choice. So really what we need to do is use Gauss's law on the inside and figure out what happens. So let's do that. So, we get past all the symmetry stuff. We just get EA equals Q enclosed over epsilon naught. And so we're dealing with the surface area of a sphere. We get 4 pi r squared. That's the surface area of a sphere. But the key point is the Q enclosed, and I think this is where we're going to run into issues. So really, with the Q enclosed is going to be the charge density times the volume. So just charge density is the charge per volume. So I'm going to assume this rho is some constant. It's uniformly distributed inside. So how does V look like with regards to R? Well, the volume of a sphere is 4 pi R cubed. So we have an R squared over here. We have an R cubed over here. So when we solve for electric field, we'll notice we'll get rho R over 3 epsilon naught. So it's actually linear with regards to R. It's linear, so it's the power of R to the 1. So there's only one that looks like that. It's actually going to be this diagram. So it goes as 1 over R and then 1 over R squared. So actually this is the same problem if you look at the gravity from Earth. So you can actually do a similar Gauss's law. So how gravity actually goes inside Earth is that it linearly falls as you get closer and closer to the center of the Earth. So eventually there's no gravity because you can think about everything entire Earth is pulling you all which way equally. So it's actually going to be, you're going to be floating inside the Earth. And the gravity is actually maximal on the surface of the Earth where we are. This is actually the highest amount of gravity we'll have. And again, the point is that when you're sitting in here, you don't have as much mass pulling you straight down. Some of it's actually pulling you this way and this way and this way. So the gravitational pull is actually less inside. Okay, it looks like we might actually have to be doing some math at this point. So charges Q1 and Q2 are on the x-axis. So let's put that here. We get Q1 at distance A, Q2 at distance 2A. So this is double. Oh, that's an A. Well, that's supposed to be an A too. For the net force on another charge at the origin to be 0, so we're going to be putting a bad boy here. We're going to say maybe it's some charge Q3. So, we don't really have to put a charge Q3 here. Maybe it's the same thing as asking what's the electric field. So it's actually the same statement as saying the electric field would be 0 there, because then it wouldn't matter what charge we put in here. The force would always be 0 if it's the electric field times that charge. So how do we make the electric field 0 there? Well, you can imagine we want to get 0, an electric field created from one and some of the other. And these are really vectors, but they're really only x components, the only things that matter. So we get Q1 K over A squared, K1 over A squared plus K over Q2 2A squared. And so we're going to have to do a little bit of algebra. So no K's, get rid of those. Subtract the other side. Q1 over A squared equals negative Q2 over 4A squared. So the 2 gets squared too. So we see we get a relation Q1 equals negative Q2 over 4. So do we have that option? It's Q2, so we got to move it to the other side. So Q2 equals negative 4 Q1. So they have to be, so this means they actually have to be opposite charges for this to be true. If they're both positive charges, they're always going to add and they're going to be pulling in the same direction. But if they're negative charges, the electric field's actually going to have to go in the opposite direction. So that's the only way they can sum to 0. And so for this bad boy, I'm picking you. Two identical point charges are fixed to diagonally opposite corners of a square. That is whatever long, each charge is whatever. How much work must be done to move one of the charges to an empty corner? Fixed to a diagonally opposite. So we got this bad boy, this bad boy. So, and we're going to move a charge here. So, okay, I just realized I misunderstood the problem. This is going to be throwing this bad boy over here. We gotta move him. That means we need to find the electric potential. It's going to be emanating from one of these guys, and it's going to be moving from a lower potential here to a higher one potentially. No, and it's going to require some energy. So we're going to figure out how much energy that would take. So it's going to be work equals change of potential. I was right about that. So it's going to be the change in the voltage times this other charge, which I'm going to keep calling Q because it's this, I don't want to write it down in the whole number. So what is the change potential? That's actually going to be a little complicated to write. So it's going to be the final one times the initial one. So I'm going to call this A because I'm lazy. So what's this distance compared to this distance? Well, may have done, equal side right triangles a little bit. We know that this is actually going to be square root of 2a. You can convince yourself that that's that, but I'm good. It's going to be k, q, the other q. So it's initially at square root of 2a minus at the, wait, no, that's the final bit. Ooh, no, it's actually at a. Ooh. A Q, all my Q's and A's are looking similar. Q over square root of 2A times Q. And that's all we got. So this looks like, we're going to move it all together, K, Q squared over A, 1 minus 1 over square root of 2. Oh my goodness, it's basically illegible at this point. Okay, then we put that in Wolfram alpha. I like writing it all at once, so it becomes, if you get it wrong, it becomes pretty obvious what happened wrong. And we get 0.131, so is that one of our options? We go and look. That looks pretty close. That looks like that bad boy, so we're gonna choose him. That's gonna be our answer. A conceptual model of aluminum trifluoride is approximately a square with charges at the corner. Cool. What is the magnitude of the electric field E0 at the center O? Okay, we're going to do a little math, and maybe we won't be able to do this one so simply, but you can sort of see where I'm guessing the electric field is going to be pointing in this direction in the end, but no. I'm guessing the electric field is going to be pointing in this direction in the end, but we will find out. We will have to do the problem for ourselves. If we just take the electric field by just a charge, it will be KQ over, this is A, so this distance, we know a little bit of geometry, is going to be square root of 2 over 2. Always double check it, but this is something I have kind of in my head all of the time. It's going to look like this. This gets squared. We get K, Q, 1/2 A, so 2K, Q over A. So that's if it's just a Q. So if it's Q, it's, we have to get a negative sign in there. We'll figure it out. And for this 3Q, we'll just multiply this thing by 3 and call it good. So the X direction, so again, what we're really doing is E0 equals E1 plus E2 plus E3 plus E4. Okay, and that's it. But we just take that equation and we take the X and Y components of that. So for E0, the X component looks like, what is E1 doing? Turns out, if you didn't know, cosine of 45 degrees is the same as sine of 45 degrees. And that's also equal to square root of 2 over 2. So we're throwing that in and using that a lot. So for E1, what direction is that? I use numbers and it's using letters, but I'm just going to pretend I use 1. Okay, it's going to look like this thing times 3. I'm just going to call this E. E times square root of 2 over 2. Is it going to be positive? No, it's not. It's pointing in this direction. It's pointing in this direction. It's going out like that. Plus, for this one, it's going to be negative. It's also going to be the charge is negative, so it's going to be 3. No, it's not 3. It's going to be E square root of 2 over 2. And what direction is it pointing? Oh, it's going to be negative because it's a negative 1 and makes the field lines going this way. Then we're going to get a positive 1 from 3. Then we're going to get another negative 1. And so for Y, it's going to be pretty similar. We're going to have to get the directions right again. So we'll add that across. What do we get? We get negative 4E square root of 2 over 2. We'll keep that in our back pocket, use that in a moment. So for Y, we get, this is also, for the X component of the first one is also going to be negative. Again, that one goes like that. It's also going to, oh no, this was a positive sign, oh no. But this one's negative, I know that. So if that's positive, did I get them all out? Let me get the signs right first. So this is going to be, this one's going to be positive. I got the signs all backwards. That's not fun. It's going to be negative and this is going to be positive. Negative, positive, okay. Where does that leave me? 4, there we go. Actually, it wouldn't matter in the end. I'm just going to get the magnitude. It doesn't matter what direction it's going. But this one's negative. And for the other one, it's going to have a positive. It's going to have positive E square root of 2 over 2. My handwriting is essentially illegible at this point. And for the other ones, it's going to be pointing towards, see, I realized I got 3 and 4 mixed up, but that's okay. I'm just going to call this one 3. That one's pointing down, so it's going to be negative. And this one's going to be negative. So it seems these two guys flip signs compared to X and Y. These guys are always going to give you the same signs. And so what happens? I get 2 negatives. I get 4e squared 2 over 2. We're going to throw that in the Pythagorean theorem in a moment. Go, essentially, you gotta get this stuff, e squared root of 2 over 2, square that. This is a negative sign. Doesn't matter though, doesn't matter. Oh, we're gonna run out of room real quick. So what happens? So essentially this 2 and this one cancel out, so you just get 2 squared root of 2. So what happens when you do that? So it's going to be another square root, get e squared, 2 times square root of 2, that's just going to be 8, plus e squared, 8, plus that, it's going to be 16 under there, 16e squared, that's 4e. Okay, looks good. So what's 4e? How I defined it? Well, that's 2q over 4 times 2q q over a. And there is one of those guys, and this one says correct. So apparently we knew the right answer the whole time because it says correct there. But we got it. We got it. That's what that is. We got it. A little bit of crazy trigonometry, but you know, there you go. Goodness, what is the of the circuit? So I think it's equivalent resistance. Now we didn't really talk about that much, but you know, let's go over it now. So for resistors in series, you just add them up straight. It's actually the opposite of capacitors. We'll talk about it at least. We'll likely talk about this in a bit. So I'm hoping we don't actually have to know this. One's in parallel, then you do the weird 1 over rule. 1 over. There we go. 1 over. You know, dot 1 over. Okay. So apparently the answer is 22, but we're going to find that. We're going to find that in a moment. So what is obvious? So it's obvious that these are in parallel. So we're going to add them together. So we have R equivalent for these 2, 3 is 1 over 5. I'm going to omit the ohms for a moment. 1 over 10, 1 over 5. So we notice we write this, we'll write all with the same base. So this is 2 over 10, 1 over 10. We're not going to use a calculator for this. We're going to do it freehand. So that was going to be, that's going to be 5 over 10, which is actually 1/2. We flip that over. That's just going to be 2. So it's 2 ohms. These two guys together, just 2 ohms. So maybe this is not actually the right answer because it's going to be 2 plus 2. The right answer just should be 4 ohms. Because when you put a bunch of resistors in parallel like this, the electrons have a bunch of different routes that they're allowed to run, so they're actually able to run more efficiently. Usually you decrease the resistance by putting a bunch of things in parallel, so it's got to be actually lower than all these numbers. So it's 2. 2 makes sense. 2 and 2 makes 4. Okay. Which of the following changes will necessarily increase the capacitance of a parallel plate capacitor? So increasing the charge, well, increasing the charge actually has nothing to do with the capacitance. That's just has to do actually with external forces. So for instance, I could just increase the voltage. So that doesn't actually mean I increase the capacitance. So it's not that one. Can't be that one. We'll go back to that one. That's probably, you know, because we know that. Decreasing the area so that we know the capacitance of geometrically is the cross-sectional area over distance. So decreasing the area seems like the bad move. We want to increase the area so there's more room, which will increase the capacitance. Increasing the distance, well, it's 1 over distance, so we actually want to make it closer, so it's not that guy. Increasing the potential energy between the plates. So it's just like the first one. We actually don't know whether that increased the capacitance was because of the increased capacitance or was, you know, just the charge being increased. You know, you see how those kind of go hand in hand. It doesn't actually increase the capacitance. And again, with the equation I'm using in my head is Q equals the change in voltage times C. So, I mean, these both could go up together, but this can stay the same, or we, you know, go down. We actually have no idea. It can't be this one. It doesn't force it, but inserting a dielectric material does. So essentially what that does is it increases this number. So if K is larger than 1, you essentially multiply this K in times this epsilon naught, and you will forcibly increase the capacitance. That has to increase it. So there's our answer. The dielectric with kappa equals 2 is inserted between the plates of a parallel plate capacitor that remains connected to a 100-volt battery through the process. Then, so picture time, you have this, some batteries hooked up, and you put some bad boy material in between there. And so, what does that mean? Well, the voltage is going to remain constant. The voltage is always going to be V. So the thing that's going to matter here is Q equals the change of voltage times this capacitance. So what happens is that the capacitance originally was epsilon naught over AD, but now it's increased to, say, a C prime, which is this kappa times epsilon naught, A over D. So you can see how the capacitance essentially has doubled. So it's going to be 2 times the original amount. So the potential difference between the capacitor plates increases. No, we actually kept the same voltage, so that's definitely not right. It's the same battery supplying the same voltage. Potential, again, that's the same. So now we have choices of charge. We have choices of charge. The charge is not going to remain unchanged, so we're going to see implied by this. If this doubles, it's actually going to have to double this, so it actually doubles the charge stored. So it's not this guy. So there's our answer. Okay, that was a lot of problems, long video, but hopefully it helps us get a little more of a holistic picture of what's going on, maybe prepare us for any type of test coming up or any type of general big problem set. Okay, good luck on whatever you're working on. See you next time. Bye.